police shooting data, we're going to demonstrate RandomForest and Ch8.
I have a question about R before you start.
Yes.
So I don't know if other students have had the problem or not, but when I try to install the RPart XSE package, it keeps saying that this package is not available for version of 3.6.2. Have you had this kind of problem for installing the package for decision trees?
Are you using a very old version of R?
No, the R Studio that I have installed, it's using the version 3.6.2.
I was able to install RPart on mine. I think I have 3.63.
Yeah, RPart works. I can install it, but RPart XSE, did you install that?
Oh, that's the book version. That's the data mining with R package. Okay, I see. Anybody had issue with that?
Yeah, I got some sort of conflict or some error with that. I wasn't able to run it properly.
Well, why don't you send the error message that you have and tell me what version of R you have?
Okay.
Yeah, I can try to look into it. I think I updated my R and everything seems to be working.
What version of R are you using? You click on Tools and then Global Options at the bottom.
Global options.
And then, okay, yours is 3.62 as well. Yeah, it's the same. I don't know why I have the problem.
Yeah. I'm sure you tried it multiple times, right?
Yeah.
Yeah. I could actually have, I can have a different fresh install of R 3.62 and see how it behaves. If you happen to have the problem solved for no reasons, I mean, sometimes I don't know if this is
Okay.
what's the glitches there might be. Yeah.
Okay. All right.
Oh gosh. I don't get to see my button down there.
Oh.
Sometimes just pressing enter seems to work for me.
Press enter. Oh, good. Thank you. Thank you. Okay, so last time we looked at how to tune, create multiple, to do grid search, to find the best performing tree. I think in this week's R exercise, there is a R performance estimate exercise. That package was also from the data mining with R book. I have tried it. It sometimes works, it sometimes doesn't. I think the method was not built very robust when you have different split of data. Certain anomalies were not treated gracefully by the package. That is the reason that I actually have this crude raw way of run things multiple times and save your models and then extract your model values and then find the best combination listed here in the decision tree R exercise, R example. But some other packages, for example, support vector machines, we're going to talk about it, but today, but probably not being able to run the R exercise yet on police shooting on support vector machine yet. It comes with the tuning function. So for support vector machines, you can use the built-in tuning that's more robust than the package come with the book. Okay, that's a side notes. Anyway, so we're going to run RandomForest on our data set. I have some graphs. Okay. So we will load our data. Again, we need to remove all those attributes with high cardinality and remove the numerical values. So we have this smaller set of shooting. Factorization is a method that I defined at the beginning. All it does, it turns every character and other things, all the categorical variable into vectors. So I'll do that. Ensemble methods are relatively time consuming, just to let you know, to run because it builds lots of trees, right? To run this. And we get our training and test data set. And now I'm going to build this tree. So it's going to take some time for the tree to build. I asked the system to build 500 trees. The importance is a attribute that you could set the value. When we set importance to be true, the random forest, when they build the tree, it also assesses the importance of different attributes to this prediction problem. So we will set it to be true. Oh, luckily, it's done. Then we can, so get score, remind you, this is our accuracy score, okay? So this accuracy score gave us the overall performance on all the classes that we have. We have, I think, 6 different race labels. Get score gave us 1 score that shows the overall performance in terms of accuracy. Oh, I have to rerun get score again. This is my get score function.
If we have importance equal to true, then is it still useful or better for us to remove attributes we think are not good or have high cardinality, or will the system automatically do that for us?
And the system will not be able to automatically do that. Not removing that will just make the system running forever. Eventually, R will crash. Because the decision tree algorithms are not very efficient when we have large cardinality for attribute. It does all kinds of combinations to find the splitting condition. So we removed those attributes that are not offer any information, for example, IDs, and those information that those attributes has very high cardinality or numerical. Our numerical attribute already being discretized into levels, so we keep the level attribute but not the raw value attribute. So we have this tree generated, we run the score, we find the accuracy score of this. So as you can see, I think our best performed tree generated 56% of accuracy. This is roughly 55. So as I said, the random forest will give you competitive results that had being much more robust. So in this case, I would choose random forest over that optimal tree. And we can also ask for the tree model to give us the confusion matrix. Remember the confusion matrix from this, you can actually calculate the here class error, remember again, is 1 minus accuracy. So every class, it computes the class error for you. But you can use this confusion matrix to compute any other measurements that you want. The next thing I want to show you is the predicted. We're going to view it in a table.
Over here, for the
Mhm.
500 trees, is that just a number that you know from experience works well, or do we need to do some kind of
Tuning. Yes,
tuning?
you want to tune.
Thank
I don't know 500 is the best number, but it's a reasonable number.
How do you come up with a reasonable number?
By looking at other people's papers.
Okay, thank you.
Oh, yeah. So predicted is the class labels for the examples. And I think for the vote, I want to show you the probability. So this here, you can actually see the probability of the predictions. Because we set the importance to be true here, we can now ask the system to actually show us this two, then give us the same information. Only sometimes when you don't use scaled, the default scaled is false. So you will see the importance, this importance and that importance generate different things. No, they are the same thing, only one is scaled. Another is not. So either one going to give us the same kind of information.
Sorry to interrupt. About the number of trees, I tried with 250 trees, 500 and 750 just to play with it, and both 250 and 750 had a lower accuracy than 500. Does that happen if you have too many trees that the accuracy is likely to drop?
I don't think so. Well, hold on. That's a good question. I don't think so.
I mean, it wasn't really very different. So 250, like this was 54.8%. 250 trees was 54.2%, and 753 was 54%. So
right.
it's
That's what
less
I was
than a
going to
percent.
say. Yeah, the difference is going to be very, very small. I think this is the power of randomization. I think one of the things that the robustness claim is coming from here, that the performance difference is, so that it's not very sensitive to the number of trees that you use when you use a large enough number. So this is the importance result. Generally, we look at these two, mean decrease accuracy and the mean decrease Gini. Above it, you also see for each class the importance of different attributes. So how was the accuracy this score was generated? It was these two measures, mean decreased Gini and mean decreased accuracy, were generally using very different mechanisms, but they all sort of tell you how important that attribute is when generating all those trees, random trees. For Gini, we know that Gini is used to split the tree, to split the node. This measures the impurity. Therefore, mean decrease in Gini will show that attributes with larger cardinality going to have a larger value. So this may not show you how predictive, the power of prediction of the each of attributes. So this measure, the mean decrease in Gini is less often used in literature to argue for the importance of attributes. Mean decrease in accuracy is a more robust measure because how this was calculated was based on, for each of the feature, the system will actually shuffle the values. So see, we have 100 examples having manner of death. So we have 100 instances of manner of death in these 100 examples. When we build one tree, we use the original training example data. And when we build another tree, we shuffle those values. We put them randomly in those 100 slot. And we see the performance difference. This is the mean decrease accuracy, how that was generated. So this is a more robust way of looking at the attribute importance in this prediction problem. We could also view them in a graphic manner. Make it bigger. So the greater the better. I'll run it again. It should generate a little bit prettier tree now. Give it more space. Oh, okay. Now it looks more reasonable. So in this example, we see poverty level, age group, and victim population ratio levels. Poverty level, those are more important attributes used in prediction. This is confirmed when we look at our trees that we generated last week. Age and poverty level was certainly included in almost all the trees that we generated.
So when we're interpreting this, the ones lower down are less important. The ones like in the graph on your right side, the plot, the attributes at the top are more important? Is
Yes.
that the... Okay.
Yes. If we look at the value here, you see the greater the value, the more important. So this poverty level has the greatest value.
But how much do we know is impacted by cardinality versus importance? How do we figure that out?
When we do the mean when we look at this is not affected by cardinality. This is the Gini index. So we can see the ones months has the largest cardinality. None of the months, none of our tree actually have months as a decision node. So you can see that the mean decrease in Gini is very biased towards attributes with high cardinality. And that is the reason that it's rarely mentioned in literature to explain the attribute importance.
Thank you.
Okay.
But here, sorry, for years in Gini, there's only, I thought there was only 3 years. How come years is high?
4 years.
Oh, 4 years.
Yeah.
So it's still high. Is that because it is still significant in some way?
It's really hard to tell. But I think all other things have a value, let's look at year. I don't remember how many years that we covered. Levels, shooting. We have year. What did I do wrong? Oh, we actually don't have level. Yeah, it's a number. So how many unique numbers that we have?
So is it high because we haven't made it a factor?
I would not think so. So this is 5. I think all our other things has 5 level to say the least. All other factors have at least 5 levels. So we can't really, yeah. But from our other trees, I think a lot of things in data analysis is verification. So here we have question about year, whether year is important or not. And we look at our trees that we generated before year never appears. And based on our understanding of this scenario, the data, if we did our exploratory analysis, we'll see year probably has very little effect on the shooting phenomena. I think we should conclude that year is not important. By looking at these 2 sets, I certainly would put more trust here than here with the mean decreased Gini.
So I'm guessing something like year, the reason, like just sort of stepping back, saying that, okay, normally we do not expect this to be significant. Is it only like perhaps significant if some kind of laws changed and therefore certain changes happened in the shooting volume or something?
Yeah, if we have other evidence. If we have evidence, then we can examine this year in more detail. I think our evidence so far is suggesting that year should not be important. The only thing that left for me to think year being treated important here is because of the cardinality.
Thank you.
So I have some sort of things that I'm still working on. I wanted to visualize the forest, but there's not a way to. I mean, it's not building. So I was looking for other people might have. Some people have created something that they claim that it can visualize a tree, but I have not been able to make it work. So ignore that. So what I want to demonstrate next is Ch8. So for unbalanced classification problem, our example, although in this multi-classification class problem, we see in imbalanced distribution class labels. But as we also mentioned that for multi-class classification problem, there is not a way for it to address this question. So I'm going to reduce this to a 2-class classification problem by only making 2 classes. So let me first run this library. So here, this part shows that Ch8 does not work on multi-class problem. So next, I drop the level to just include A and Asia and white in our data set. We have this many rows now. Our race distribution is we have 61A and 1500 of W. So now we're going to do Ch8. So I made it here. If you use help Ch8, it gives you bad information. You have to go to the documentation, our documentation, find the PDF file, and to understand how to set the parameter. So update this. My old run. This is from my old run. But the idea is this percentage over, this control how many examples that we're going to oversampling for rare class, minority class. And this percentage under is going to control how many majority classes we're going to sample. So read this note very carefully. When we set this to 1000, the system is going to divide this parameter by this parameter. It basically says for every rare example, generate 10 new examples. If we generate 10 new examples, our new example going to be what? We started with 61. Then for every one of them, we generate 10 new examples. This is going to give us 670A, right? And then here are the number under. For the majority class, we're going to randomly select this number times this divided by 100. So if we're going to have 200 here, it's going to be 670 times 2. But we have 100. 100 divided by 100 is 1. So this is going to be, so this is we are going to expect with this mode output. So we have, for each numeral, generate, this is for each new example. So this should be 610. For every new example that we generated for the minority class, we generate 1. We select 1 from the majority class. So are you still with me? I hope I did not confuse you. So K is the parameter for the nearest neighbor. K asks the system to consider the 5 nearest neighbor, but exactly how those 5 nearest neighbor are going to be used is determined by how many examples we're going to generate. Here we generated 10 new examples, then those K nearest neighbor will have to be used twice. So we have this new data, and we can see this new data has some duplicated data. So now we have this this is my study code. You can probably ignore them. So now I'm going to use our new balanced data set to do this classification against and see how the system is going to perform. So we generated our I part. Run this. O tree is the original tree, and the B tree is balanced. And we're going to test those on our reserved data. We get the score. We can see that the balanced data is worse, measured by attributes. But as I mentioned earlier, when we do imbalanced problem, we don't care about attributes. We don't care about accuracy. We care about recall. So I'm going to use another library to help us to compute position and recall. So this is from the book. We get this prediction. We table that. So this is the original, right? So in the original, we can see we have a total of 15 A's, only one being identified as Asia. This is our minority class. You can run this to get your position and recall scores. Position and recall score, recall is very, very low. When we do the balanced data set, we can look at the table. From the confusion table, we already see a lot of more Asia cases has been identified. So our recall is improved. So we can also do the generate recall. Recall increased from 0.06 to 0.6. So it increased by 10 times.
When the precision drops to like 5%,
yeah.
What is the intuition behind that?
The intuition, position and recall always has this inverse relationship. When you increase recall, position will always drop. That is why the position and the recall curve has to, well, yeah, when you look at the curve, you will see how that goes. Think about the system. If you think, I often explain this using diagrams. I can't really draw diagrams here. The key thing to remember is the learning algorithm, because we don't want them overfit. Therefore, the decision boundaries, they cannot draw those very precise decision boundaries, only pick out good examples and leaving out bad examples. If you think of, we can have very high precision by using a very small circle, cover only the positive examples. That will give us precision. Think about those examples, probably going to gather together because they belong to the same class. When we increase our circle, we bound to going to include more examples into our decision boundary. But some examples going to be correctly predicted, others going to be incorrectly predicted. Therefore, when we increased the boundary very wide, now we have recall increased by 10 times, we definitely have admitted some of the bad examples that hurts our recall position.
So does that kind of say that because in the denominator is now going bigger, so the true positives are there, but we're getting a lot of false positive.
Exactly.
And I'm assuming false positive here means the record or the observation was white, but was classified as Asian?
Yes. Because we want to find more Asia, so we expand our decision boundary. We draw a larger circle. That larger circle includes lots of non-Asia that we think they're Asia. We increase the recall, decrease the position.
Okay, thank you. I mean, clearly with the harmonic mean would show this is better because it went from 10 times better recall and only, 30.
Right. But when we deal with imbalanced problem, we will not use F1 score. We'll look at recall.
Okay. Now, So what about F2 score in this case, or still just better to use recall?
That's a good point. It really depends on your situation. What is your optimization goal? You could use, in terms of using which measurements, I think one concern is because every time when we develop anything, we want to compare our system with others. If nobody else use F2 score, then you probably don't want to use F2 score because you can't compare your result with others. Yeah, it's just one consideration. Yeah. Recall and position is fairly easily when we plot the position recall plot. It's very easy to see the difference. So the position recall plot used probably more often than F2 score.
I have a question.
Yes.
Is because we have now 10%, no, 10 times more recall. Is and we choose to have 10 times more Asian in there. Is there a relationship between there? So if you were choosing 20 times more Asian to put in there, would it be like, no, couldn't be.
I think it's measured on the test set, and test set, I think, I don't know, Professor, is test set still original data, or is test set have more Asian data?
No, test set is original.
Ah, okay, I see.
Yeah.
And another question, if we have, I'm a little bit confused about what is positive and negative if we just have more than two.
Oh, yeah, good question, very good question. This is, so here, this classification matrix, there's many other metrics. You always have to pay attention to their menu. So we tell the system all class is the system default and make the first appearing class label as a positive class.
Mm-hmm. Okay.
There's also a parameter that you can just say pause class.
Okay.
And say that's A.
But if you have more than two classes, what is considered positive or negative? So
if you have more than two classes, you will not get the position recall scores.
Okay, I see. Okay,
you get accuracy, macro, whatever. So those.
Okay.
Yeah.
Thank you.
Yeah, sure. I think this made my points. That's all. The other notes is about, I think I already emphasized it. It's not because two classes have different numbers, you would just automatically consider it to be an unbalanced classification problem. Really, the unbalanced classification problems means we care about one, the minority class. As you can see here, we sacrificed greatly on position to increase the recall. So it's not whether the classification problem is unbalanced or not is not only determined by the class label distribution, but also really more important, determined by your intention. What's your goal? What do you want to discover? Okay, if we don't